this one here. So 6 faces, 8 vertices, 12 edges. Good old cube, the really good old cube. And the first thing you want to ask yourself is, what can you possibly say for an hour about this? Right? Well, let's show you something. There's 4 books about the cube here. Some quite recent ones. So this is a very learned book just put out by Cambridge University Press. It's all about cubes. The one up there, Graphs and Cubes, is also an academic publisher basically a couple of years ago, all about cubes. And then some older ones. I've got one here, Curiosities of the Cube, and the cube made interesting. And actually, there's going to be a 5th one, which I'm going to write. It's going to go right there. It's going to have very little overlap with those other 4 books. All right. So what was the starting point to all this? I mean, I'm a geometer, I'm a mathematician, and I've been basically living mathematics for years and years and years. And one of the most surprising things for me is that I come across facts about the cube that I didn't know about on a fairly regular basis, and facts that are actually really, really interesting and amazing, to me at least. So today, I'm just going to give you a couple of examples of these things that I came across over the years. And I'm going to start with the last one that really prompted this current obsession with the cube. Just last Christmas, I came across a fact that I didn't know before. Okay, so just to make this a little bit more interesting, let's just assume there's a huge, giant cube entering the solar system, and so it's approaching Earth, and eventually it's going to hover above a plane somewhere. Okay, so hovering above a plane, so a huge cube hovering above the plane, and the sun's right above, and the sun's casting a shadow, right? So it's basically this kind of scenario. Obviously, the cube can be positioned in space in many, many different ways. It's going to cast lots of different shadows. And now we're going to measure 2 things. The first thing we're going to measure is the area of the shadow, and the other thing we're going to measure is coming prepared here. The other thing we're going to measure is the difference in height between the lowermost point, the bottommost point, and the topmost point. This is the height difference. Okay, now let's just say this cube has a side length of 1 kilometer. Okay, we measure the area, measure that height. There's a very surprising correspondence between the 2 values that you get here. Does anybody know what the correspondence is? They're equal, always. So if you measure height difference 1.3 kilometers, then the area down here is going to be 1.3 kilometers squared, exactly. And it doesn't matter which way you position the cube in space, it's always going to be the same. Now, did anybody hear about this ever before? No? Well, this is a fairly new fact. I actually tried to trace it down when it was discovered, and I found a paper in 1985 where somebody writes about these sorts of things. And actually it gets a lot better. Like for mathematicians, when mathematicians talk about a cube, they do not only think of just a cube here in our 3-dimensional world. There's actually cubes in all sorts of dimensions. There's 4-dimensional cubes, 5-dimensional cubes. There's also a 2-dimensional cube. What might that be? 2-dimensional cube? A square. So, and the same sort of thing works for all these kind of cubes. So we could have a 4-dimensional cube, for example, whatever that might be. You cast a shadow into 3 dimensions that's some solid. You measure the volume of this thing. You measure some sort of height difference in 4 dimensions. And that volume is always going to be exactly the same as that height difference, as long as you start with a unit cube. Okay? Okay, so that was my first really amazing fact. And I thought, yeah, more people should know this, so that's why I did this talk. Could actually go now, because I think if you remember this one, I'm always already pretty happy, But now, let me ask you some questions. There's actually a nice application to this. We could have a look at extreme shadows. Okay? So you want to figure out, among all the shadows that you get when you position a cube, which one is the one that has least area? How would you figure that out? It's actually really easy now, because the only thing you have to make sure is that the height difference is least. So how do you make sure that the height difference of something like this is least? So how do you position this thing in space so that the height difference between the topmost and the bottommost point is minimal? It's very simple. It's easy to see. What do you do? Exactly. Just put it basically like this. Yeah? So it's just here parallel, and then the shadow is going to be a. It's just going to be straight. What about maximal shadow? How do I get the maximal shadow? Maximal shadow I get by what do you do? Oh yeah, you got the right idea. So it's kind of diamond shape, but the diamond shape for a cube is like this, right? So if you look at the long diagonal here, if you make this sit perpendicular to the ground, you get the maximal shadow because then this difference here is maximum. What's the shadow? What does it look like? Does anybody know what the shadow looks like when you do this? Yeah, it's also a bit surprising. Not many people know this, but if you position it like this and you look at the shadow, you get a perfect hexagon. And you can also figure out what the area is. If this is one kilometer here, then this is 1, this is 1, this is 1, and then the Pythagoras, 1 squared plus 1 squared plus 1 squared is 3. Square root of 3 is, well, that's the area. Okay, so pretty good fact. So on a scale from 1 to 10, what do you think amazing? What about is it an 8 amazing, or 5 amazing, or root 3 amazing? That's not very good, unless we make 1 really good. All right. So let's move on. So here's another one. This is a classic. This goes back 400 years, and despite the fact that it goes back 400 years, hardly anybody knows about it. It's about. It's called Prince Rupert's cube, and Prince Rupert is the guy over there on the left. And well, he was a general, and his business was basically killing people. He was a statesman. His business was killing other people, and well, he also got into killing cubes. So his idea was. Take a drill and drill a hole through the cube. Okay? So if you do this, then maybe you'll be able to kind of fit a small cube through this hole. So the small cube could fall through the hole, and so you could fit one cube through another cube. Now his question was, what's the largest cube that can fit through a hole in a given cube? So what's the largest cube I can fit through this guy here? So I can drill any cube, right? The whole thing shouldn't come apart. What's the largest one I can fit through? What do you think? About half the size, or 3/4, or like this? Can I make it bigger than this? Pretty obvious, right? But how big can you make it? How big can you make it? The answer is actually quite surprising. And to give you the answer, I go back to my shadows, okay? So here's my two shadows again. This is the maximal shadow, but you can also think of it as kind of you're looking at the cube from a special perspective. You basically look at the cube from far away, so that the diagonal is just pointing towards you. Then you see exactly this, right? And then I've got a second copy of the cube, positioned so that you actually see a square. And now what I do is I just bring this guy here in front of that one here. Okay? And well, how do I drill a hole now? I basically just take the square that I see here and drill straight down into the other cube. And that gives you a very strange hole, and through that hole, how big a cube can you fit? That's very good. As big a cube as the one you started with, that's exactly right. So I actually a couple of years ago, I got into 3D printing, and this is a very kind of nice model. Here's two identical cubes, and one of them, there's a special hole in here. So there's the hole. So it's still kind of hanging together. And now I'm going to try and fit this other cube through. So we go. You can see it fits through. So you can actually fit one cube through another cube. And actually, as you can see, there's still a bit room to actually make it a little bit bigger, right? So it's not coming apart. So I could actually make the hole even bigger. And so the inside here is I can actually take a cube, make a hole in it, fit a larger hole through, fit a larger cube through this cube. Pretty amazing. So which one do you like better? First amazing or the second amazing? You like the second amazing? Mind blowing. That's what I want to hear. Yes. All right. So just in big, just in case you couldn't see it. So that's the hole in the cube here, and that's That's the cube pushed halfway through. Okay, now comes a question that all of you should be able to answer, because you do this all the time. I mean, you've been playing with cubes since you were, well, 0, right? Okay, how many sides can you see? How many sides of a cube can you see? So if you look at a cube, how many sides can you see? So at the moment, so the cat's looking at the cube. How many sides does the cat see? Three, above 3, yeah? Well, there's a trick. I mean, there's one trick. If you look at a cube like this, how many sides do you see? So, okay. So now let's make non-transparent sides. Okay, non-transparent sides. Let's say this cube. How many sides can you see? 3? Yeah. Can you see more than 3? No? You could try looking at it like this. How many do I see? Well, maybe like this. Well, maybe if you don't see it with this one, I could do it like this. That's how many do I see now?
5.
5, I see 5. So if I look at it like this, I can actually kind of lean on this one, lean on this one, lean on this one, lean on this one, lean on this one. 5 ways of looking at it. I claim with a non-transparent cube you can even go up to 6. How do you do this? What do you do? No mirrors allowed. Mirrors are out. But yeah, why? I mean, I didn't say no mirrors, so it's a fair answer. But let's just say no mirrors. Still, I want to see 6 sides. How do I do this? No, make it really big. So at the moment we're sitting in a cube actually. When you think about it, we're sitting in a cube. The sides are non-transparent. If I sit in that corner over there and just look up here, I actually see six sides. I think it's a fairly good thing to know. So next party, you know, ask your guests, how many sides of a cube can you see? Huh? It is, it's like a cube, exactly. Okay, third amazing fact about the cube. Oh, here's another one, a bit more difficult. Here we've got another old... We can prove that you can do it in a second because, well, it is stuff. Okay, what we've got here is a really, really old puzzle. It's the boy, the wolf, the sheep, or the lettuce puzzle. Sometimes the sheep is also called a goat, and sometimes the lettuce is called a cabbage. But apart from that, everything kind of stays unchanged. I've got actually 3 candidates here, so I'm kind of, oh, you're the boy. This Tweety thinks you're cabbage. This one here is the wolf, and this one here is the sheep. Right? And now we arrive at one side of the river, and I'll just make a river here. So there's a river. And we have to get those guys across. So get them across. And the way this is basically my treasured possession as the boy. And I've got this boat. And the only restriction here is I can only ferry one thing at a time across. Okay? So that presents me with some difficulty because if I take my wolf and kind of cut that one across, what's going to happen on the other side? The sheep eats the lettuce. Right? So we don't want to do that. Same sort of thing if I take the lettuce and ferry it across, what's going to happen? What's going to happen? The wolf eats the sheep. So that's not good either. So what do we have to do? What do we have to do? The sheep goes first. Sheep actually tiger. Okay, so the sheep goes first. So that's really forced. How do we continue? So you get one go, and then somebody else has to put one go. So what do we do next? So I'm this. Okay, I'm this. I'm here with the sheep. What do we do next?
You can take either one of the other 2 across.
Okay, we'll go. Okay, you take anyone?
Yes.
Which one do you want to take? Lettuce? Okay. So, okay. Lettuce. Now, what do we do next? Somebody else. Yeah, what do we do next?
Next, you go back and take the sheep across.
Okay, we have to take the sheep across because otherwise, if we just go back on ourselves, it's going to eat the lettuce, right? So that's not good. So we take the sheep across. Okay, now what do? We take the wolf. Okay, we take the wolf. This is over here. Okay. Now they can stay together, right? They don't do. The lettuce is not going to eat the wolf, right? Now we go back and take the sheep and take it across, and we solve the puzzle. So that's a real, like this is a real classic, right? It's a real classic. But you can actually kind of get a really good sense of what's going on, like a kind of a full picture if you look at this in terms of a cube. Okay, so let me just show you how it works. So I'll just call this side the 0 side and that side the 1 side, okay? And then, if you just look at where we can be with these 3 different possessions, distributed among the shores of the river, and then we get different states here. So, for example, at the moment we've got the sheep over here, and the wolf here, and the lettuce here, so that means it's 0, 0, 0 at the moment, okay? And what we want is, we want 1, 1, 1, okay? The first move was to take the sheep across, so that state is noted down as 1, 0, 0, right? And if we had taken the wolf across, it would have been, well, barring that somebody beat somebody else, 0, 1, 0, okay? So how many different ways of putting zeros and ones are there? So the first position there's 2, second position is 2, third position is 2, so it's 2 times 2 times 2 is 8, just like our cube. And actually if you look at these things, 0, 0, 0 as coordinates, you get the coordinates of a cube in space here. So that's the coordinates of a cube in space. And now it turns out that the edges in this cube, they correspond to possible transfers here. So for example here we go from 0, 0, 0 to 1, 0, 0. That's just me saying that, well, these 2 guys stay where they are, and we take the sheep across, okay? So this means we take the sheep across. So this cube summarizes everything that basically can happen in this system here, okay? And, well, let's just have a look. All these guys here, all the black transfers corresponds to sheep going across, all the red ones correspond to wolves going across, and all the green ones correspond to lettuces going across. And basically we get from one side to the other, we go for a walk on this cube, except some of these transfers you shouldn't do, right? So for example, we shouldn't go this way, because that's taking the lettuce across, and as we take the lettuce across, somebody gets killed, right? The sheep eats, no, the wolf eats the goat. Or this one is also not good. So if you actually take out all the bits that don't work, we're left with this part of the cube, and then a solution to the problem is just going from here to there, right? And there's really 2 main, essentially different ones. So this one is forced, we've seen that, it's a sheep going. And then you have a choice, either the lettuce goes, or the wolf goes. Now if you continue this way, then everything's forced, basically. Right? If you go that way, everything's forced. There's really 2 essentially different solutions to this puzzle, and you can see it by looking at it in this cube shape. Just go again, so there's a sheep going across. Okay, now we want to do the lettuce, but we're on the other side of the river, so we first have to go back. Now we take the lettuce across. Okay, now we want to take the sheep across, well, we're on the same side, so we can do this straight away. Now we want to take the wolf across, we'll just do this. Now we've got 1 more to go. So going back, and we take the sheep across and finish. And I've just shown you a picture of another book up there. Actually, if you kind of scroll back here, or it might not have been such a good idea to scroll back this way, so let's just do it fast. I had all these cube books at the beginning. There is actually a book about this puzzle too, so a whole book about the puzzle. That's a really boring book, but I bought it anyway. So there's this other book that I have here, which is a little bit more interesting. I'll just scroll through again. It's Graphs and Cubes, and it's basically about these, it's kind of these higher dimensional cubes that I mentioned earlier, interpreted as these 0-1 sequences. So it's like 300 pages of this stuff. Right? This is kind of one of the this is one of the most basic examples, but a pretty neat one. All right. Okay, here's another fact. Let's just look at this one. So this goes back to 2010. So in 2010, me and the family was back in Germany watching the Germans win the Soccer World Cup, well, almost. Anyway, but everybody was kind of obsessing about soccer at the time. And, well, in the supermarket they sold strange kind of soccer balls, and all of a sudden I saw a cube in a soccer ball, which I had never seen before. So I mean, it's a soccer ball, it's the usual kind of soccer ball. Do you see a cube in here? Do you see the cube in here? It's a bit hard to see the cube in here. But it gets easier when you buy something like this from the supermarket. They had these in the supermarket, they were everywhere. You can actually see a cube very well in here. So the difference between these two balls is it's exactly the same hexagons and pentagons thrown together in exactly the same pattern, but in the traditional soccer ball pattern, all the pentagons are colored black. In this version here, some of the hexagons have been colored black. In fact, it's just 8 of them. If you just look at it like this, you can actually see they make a square here. They make a perfect square. If you look at the centers of these hexagons, they make a perfect square. And if you go around, there's another square, they make a perfect cube inside the soccer ball. That's weird, isn't it? Is this mind-boggling? Or you still like the whole better, right? You like the whole better? Or is this, don't know yet? Okay, so just to boggle your mind a little bit more, I'll just tell you, you can actually find even more cubes in here. So we've just used a few of those hexagons to make that cube. If you use some of the other ones, we can actually find 5 in total. So there's 5 cubes in total hiding in the soccer ball. And I'll show you all at the same time. That's the 5 cubes hiding in the soccer ball. And just, here's highlighting where they are. So this is the one we had first, right? And there's 5 more hiding here. Pretty good. Oh, I've also got a 3D printed, or 3D printed. You can have a look at them. Do you want to just pass them around? Yeah. Okay, so what else can we see in here? Well, can you see the pentagrams? So all there were worshippers here. Can you see the pentagrams? Can you see them? There's lots of them. Okay, but anyway, I just highlight some of them. So there's the pentagrams, but the pentagrams are surrounded by pentagons. And so if you look at all the vertices of this compound cube thing, you actually get this shape here. And this is one of the famous 5. So one of the famous 5, one of the platonic solids. I've got all of them here. There's 5 of them. The cube is one of them. The dodecahedron is another one. There's this diamond shape here. This one here, icosahedron. And then you've got the pyramid, like that. The famous 5, they basically have been, these were incarnations of spatial beauty, and people have been obsessing about them, like Plato and really famous guys like Kepler and other people. So really, really important stuff in mathematics and geometry is basically the mathematical supermodels. Here they are. So there's one of them in here. And of course, if you just highlight one of the cubes in here, you can see that this supermodel here is made by basically putting roofs on the sides of the cube, right? So like that. So you have a cube, and you just put these special kind of roofs on the sides, and in some miraculous way these faces here combine with those of the pentagons. Very strange. And if you just think about it, just kind of put the roofs one at a time, like this, you get actually just an ordinary house. Right? So an ordinary house looks just like this. Right? You put a cube, put a roof on top, but then mathematicians go one step further. We put roofs on all the sides of the house, right? And we get this amazing thing. Right? So it's really amazing thing. So cubes also in there. So as I said, I mean, before 2011 or 10 at this Soccer World Cup, I actually didn't realize that there was cubes in there, but I wasn't really that surprised to find it because like in pretty much everything that you can think of, spatial, with lots of symmetries, you find these cubes. Just a little bit of an application of this little fact here. I've got all these Rubik's cubes here, and so that's a 3x3 Rubik's cube, that's a 2x2, that's a weird one, it's called a cube. And here's like puzzles that look very different, but are basically exactly the same. And how are they exactly the same? Well, just think of like one of those guys inside a dodecahedron, and then you extend all the cuts into the surrounding body, and then you get this puzzle here. So the same thing here, right? So you have a cube, extend, put roofs on, make the bigger body, and then you extend all the cuts here, it's 3 of them, and you get this other puzzle here. It looks completely different, but it's structurally the same. And there's another one here. Anyway, let's just move over this. Right. Right. And just a couple more. So these are all examples of really, really symmetric shapes in 3D, and basically all of them. Right? I mean, if you have a competition, like which ones are the best, these are the best. Right? So everybody kind of agrees on this, and all of them are full of cubes. So in many ways, the cubes is really some sort of evil puppet master. You know? Pulling the strings in the background, it's just everywhere. Right? So whenever you see something, you think it's not there, but it's there. Just quickly, where's the cube? So for example, this guy here, right? Doesn't look like a cube at all. Does it look like a cube? No? No? Okay, so I'll just teach somebody how to find a cube in here. Who wants to be taught to find a cube in this one? I think we'll have this candidate here. So, candidate come out? All right. We can do all this on your own Rubik's cubes at home, right? Okay, so the first thing the candidate has to do is, he has to grab the cube between two of the corners here. So grab the just like this. Okay, cool. Then we could grab it on the other hand like this, but we're not going to do this. We're going to actually twist our hand and grab it like this. Okay. Okay. And now I'm going to take the cube away, and you're not doing anything with your fingers. Okay, wait. Just look at the fingertips here. Look at the fingertips. There's 4 fingertips, and they actually trace out a pyramid. Now, there's a triangle. There's a triangle, and so you can find. Very good. Thank you. So like this, right? Just hold a cube like this. So I mean, most people after a couple of days they kind of get messed up and they just hold it like this. So you have to hold it by diagonal like this, and then just across like this. That's pretty good. So they've got it. There's one, and of course there's another one there. So that's the second one. And if you put them both together, it forms something called the stellar octacular, which is quite nice. That's got another twisty puzzle. And now I'll just show you a really nice picture, Escher picture, where this has been incorporated. So there you see like 2 worlds intersecting. One is kind of a, there's all kinds of dinosaurs here, there's kind of a more modern world. And if you highlight them, you can actually see those 2 guys together. And there's the cube here. And there's one of these worlds. That's a pretty nice picture, I think. Here's something else which just came up a couple of years ago. It's called a switch pitch. Who's not seen this? Who's not seen this? Never ever? He had one? Okay. Well, when it first came out, I think they appeared in Melbourne in the reject shops. And it was actually, for weeks, there were shelves full of these things. And why were they full of these things? Because people couldn't figure out what they were good for. But anyway, I bought them all, so I take a chance. Okay, so just in case you haven't seen this yet. So what happens is, wait. Right. Okay, so I just throw this up in the air, okay? And it changes color. So it throws up in the air, change color, change color, change color, change color, change color. Pretty amazing thing. And it's actually based on the fact that there's these little pyramids hiding in the cube. And you can actually kind of see this. So just look at it from this perspective. Actually, let's just go next slide. Right. So if you look at the outside, basically these wing-like things, and there's buttons. And at the moment, there's actually 4 buttons visible. I just put my fingers, there's 3, and then there's one on top. So there's this shape button configuration. 3 at the bottom, 1 at the top. And then if you go like this, there's another 3 buttons. So 1, 2, 3, another button on top. And if you kind of go in between, you can kind of see the 4 buttons here, they make up a cube. And just got to put some movies here. So this is the thing kind of turning inside out here. At the bottom, I've actually taken off the wings, and you can see what it looks inside. And you can kind of see the cube at the moment with the 2 pyramids highlighted. And when the switch pitch changes colors, it's actually the pyramids kind of, one pyramid kind of collapses in, the other goes out, and the other way around. So it's quite visible here. So here the cube is quite visible here. So it's 1, 2, 3, 4, that's a square, and that's another square. So get one of those. Get one of those. Everybody should have one. Well, I have about 100, I think. All right. Okay, so we found something. Here's another one. if you look at the intersection of those two guys, you actually just get this one here, which is the diamond. Which is the diamond here. Okay? And so how does the diamond correspond to the cube? Well, if you look at all the midpoints of these faces of the cube and connect them up, you get the diamond. But another one of the famous slides down here, if you want to know how this one is associated with the cube, you go to Martin in my web. I could tell you now, but you know, you're supposed to kind of do some follow-up reading here. So you go to our website, and this week's article was about soccer balls and other things. So you can actually find out lots more things. Okay, just a couple more things here. Cube. We'll do something else. I take a cube and I chop off the corners. Okay? So let's chop off a corner. What do I get? I get this guy here. I chop off more corners. I get this guy here. I chop more off. I get this guy here. And I chop more. And I'm back here. But now we're doing chopping off while we're having a couple of cubes together. We can actually pack this whole room with cubes, right? And what you have to imagine now is we're doing chopping off the corners simultaneously. So there we go, chopping. And then as we chop, here in this packing, there's these voids that come up. Okay, so these voids. So what do the voids look like? Well, the voids look like this guy, this diamond here. So we've got this one here is the chopped off cube, but when you put those together into a packing, that in the voids you see these guys are coming up. If you chop off more, the voids are still filled with the same guys. Now it gets interesting. In the next chopping off step, the voids actually start looking exactly like the chopped off bits. So there's this special solid here, and then if you chop off more kind of things, the voids and the solids have changed. Swapped roles. A nice one. There's also a really nice application on this one, which you've all seen before. I'm going to show you that one too. Okay, so you've probably all seen these sorts of puzzles. No, that's fine. That's another cube turning inside out, another shape turning inside out. Have you all seen this one? Yeah. Well, just imagine. Okay, let's just say. So that's our original cube. We cut into like 8 pieces like this. Okay, that's actually 8 pieces, 8 little cubes fitted together with hinges, and then we do the turning. What happens if you actually chop off the corners and then glue it together, just like the cubes before? What do you get then? Well, you get this shape here. You get this shape here. And now this is glued together in exactly the same way as the cube before. So when you actually turn this one here, it turns into a cube with a void inside. Yeah, so that goes like this. And I mean, one thing that kind of gets lost in these sorts of presents that you get every once in a while is what really happens here. So if you look at this cube, which I've just made myself, you see everything's white here, okay? Now this little cube here has 6 sides, 3 of them are white at the moment. When I turn this inside out, it goes completely black. So it's really, every cube here has 3 black sides and 3 white sides. And as you do the trick, and you're going to go further, it turns inside out like this. That's a really, really nice trick. Okay. So there it is again. Let's play them simultaneously. So there. It gets even more impressive if you use this one here, but you can get around to doing this. Yeah, you can actually cut corners off again. We're not going to do this. Anyway, so this was all really, really pretty stuff, right? Pretty stuff. Now, if you actually want to explore further here, we've got an expert here. It's Rob, who's sitting over there. Just made it. And he's the author of a really amazing piece of software that allows you to play with these things, but not only that, also kind of make them for yourself. Right? So it's nothing beats actually making some of these things and holding them in your hand and playing with them. You've got a question? Or are you stretching? Well, there's one version which is free, right, to suck you in. And then, once you're completely addicted, there's 2 extensions there, but they're pretty affordable. Anyway, So this program there, it's been developed for 50 years, 20 years. How long have you been working on it? 12 years. 12 years. 12 years, gone through lots and lots of different versions, and I think there's agreement all over the world this is the best program for visualizing these kind of symmetric solids. And yeah, the author, Rob, is here from Melbourne. This is pretty amazing. You know? So in some ways, Melbourne is the capital for this sort of stuff. Right? So check out his stuff. And I think he's got some models here, which if you watch it, maybe I'm just going to keep talking, but you can just put them here. And then once we're finished, you can actually have a look at that. Okay? So, all right. Oh, he's going to bring one of them. So he's just got one of them, which is kind of a weird one. There's this shape here, and I think he's going to show us a model where you take a cube and then kind of make a void in it. It's just this shape here. So these are all done by hand, right? These are all done by hand.
Yeah, printed out on the program.
Yeah. So that's absolutely perfect, right? Perfect. I mean, even my 3D printed stuff can't beat that at all, right? Yeah. So this is this model. So it's all done by hand, and you can do this all by hand if you get hold of, like, say, the free copy of this program. It actually prints out templates for this. You can also make new models, all sorts of stuff. It's a really good one to have. So it gets pretty mind-boggling there what he has. And it's just the ones you could fit in this box, I'm sure. Because I've seen even bigger ones. I mean, like the one he has there in his hand there, up in the pictures, is just really amazing. Anyway, so have a look at all these things later on, and I'm sure Rob's going to stick around a little bit and ask you questions. All right, wow. So that looks all like lots of different stuff together. Okay, all right. So let's move on. Now, who is familiar with Mathletics? Who doesn't know what Mathletics is? Who doesn't know what Mathletics is? All right, so Mathletics is one of the main tools for teaching maths to kids these days in Victoria. So, like, my kids always get Mathletics homework every weekend, pretty much, and it's a computer-based system. So you get questions asked, like this one is a fairly standard screen, right? So it's like one set of questions, it's like 10 questions here, and well, you've got to answer them, right? You've got to answer them. Usually I sit down with them, and it's kind of a nice launching pad for just exploring maths and getting things right. Okay, so here's a question. Click on the rectangular prism. This is like last weekend, right? Last week. So which one is the rectangular prism here? Which one? The one on top. It's pretty obvious, right? This one. Well, actually, there's another rectangular prism here. The cube's also a rectangular prism. So let's click the cube, okay? Wrong. Okay, so Mathletics. This is the warm-up, okay? That's, you know. I actually have gotten in quite a few fights with them already. And this will be a big one here. All right. Now, what do these things actually have in common? Like this picture and the other picture. What do they have in common? What do they have in common?
The rectangular prism is twice as big as the cube.
That's a very good observation. That's why we all think that one has to be the rectangular prism. Now, what do they have all in common? What do they have all in common? Well, I mean, they kind of produce kind of the same way. Okay, now let's show you how to produce them. Okay, pick a cube, pick a point. Okay, pick a point. Then pick any sort of direction, right? A certain distance. It's like a vector. Okay, so we go there. So we take the point, make a copy, and connect corresponding bits. Now we take those two bits, pick another direction, another length, and take a copy and translate this over, and connect corresponding points in here, like that, the rectangle. Or, well, not yet. Wait. Now we take two of those guys, new direction, two of those guys, connect up corresponding bits, and we get a cube. All right, so we can actually, you know, if you choose these three vectors here differently, like this one here, you make this picture, or if you make it this way, that picture there. Well. So which one is a cube? Which one is a cube among those three?
First one.
The first one, you like the first one? Because Mathletics only draws cubes like this. It means this has to be a cube. What about the other ones? Do you like the second one better? Alright, what about the third one?
No, that's too squishy.
It's too squishy?
Yeah. Too squishy.
So, okay, well, whatever. Well, in what sense is anything like this a cube, right? I mean, at the moment, none of these is a cube. I have to break the news to you. None of these is a cube because what it is? It's a picture of something, right? It's not a cube. This is a cube. Right? This is a cube. That's a picture of a cube, if anything, right? So in what sense are these anything? Okay? Well, I mean, one thing you could do to produce something like this is you take a transparent cube like this and hold it into the sun. Okay? When you hold it into the sun, you actually get a shadow of the edges that looks pretty much like this. And I mean, this is actually a common way of making pictures of cubes. You just project them like this. Okay? And then the question is, well, if you've got a transparent cube like this and you've got the sun somewhere and project onto a flat surface, which of these are actually possible? What do you think? Which of these are possible? Any of them? You're exactly right. All of them are possible. In fact, anything you can start with, you can make as a real shadow of this guy here. So choose any three vectors, any three lengths, produce a picture. I can hold this guy here into the sun so that you get exactly that picture. It's pretty good. So it's a very famous theorem. Also, very few people know about this. Okay, but now that we're equipped with this, let's answer the next Mathletics question. Click on the cube. Alright. So, okay, well, that's fine. That one over there is definitely a Mathletics cube, that's fine. But actually, in terms of mathematics, do we have a second cube here? That one is also a cube. I can hold this thing here in the sun, so that it looks exactly like this, right? So there, of course, then we click on it, but it's wrong. But it gets better. Right? No. You may think, I mean, I'm just nitpicking here, but no. Let's have a look at this one. What pyramid am I? Am I a square pyramid, a rectangular pyramid, and a pentagonal pyramid? I mean, pentagonal's out, right? But is it rectangular or square? How will you figure that out, right? Well, no. I have a smarter way for it. We compare it to the rectangular prism and the square prism. So if this is a rectangular prism up there, right, if this is supposed to be a rectangular prism, and that's a square prism or whatever, then a cube, what is this? Is it a rectangular? Is it a rectangular pyramid or a square pyramid? Come on.
Rectangular.
You want rectangular?
Yeah.
All right. Okay?
It's the same as
Wrong. Rectangular is wrong. It's not wrong. It's obviously a square pyramid, right? It's obviously a square pyramid. Okay, let's move on to the next slide. Which one is a square pyramid? Wait. Compare it to this one. That was a rectangular. That was a square pyramid, right? Square pyramid. Which one's the square pyramid? Bottom or up? Bottom one? Wrong. The upper one is the square pyramid. And why? Because it's blue. Well, this is just one session, right? One session of Mathletics. This is amazing. Okay, here, which shapes have symmetry? No. If they say all of them, you're wrong. The one on the left doesn't have symmetry. The chair doesn't have any symmetries. Surprising. It does, but not in Mathletics, okay. What about, which shape has 4 lines of symmetry? Which one?
Square.
Yeah, that's true. The square has 4 lines of symmetry, but that one also has 4 lines of symmetry. That one too. It's got more. It's got 4 lines of symmetry. So anyway, if you do this one, it's right. If you do the other 3, it's wrong. The other 2. Anyway, so if you really try hard giving correct answers that are then marked as wrong, not a problem, right? So for example here, all these questions were answered right mathematically, but marked wrong by Mathletics. So it's going to be a really... Anyway, so enough of the rant, let's just move on. Now I was kind of mentioning these higher dimensional cubes, right? And I don't really have any time to go into these a lot today, but at least I want to show you some pictures of them, okay? And actually the pictures we can make, but that's kind of continuing where we stopped here. So how do we continue to make a So at the moment we've got a kind of a shadow of a three-dimensional cube. How do we make a shadow of a four-dimensional cube?
I don't know.
Doesn't matter, we just make it anyway. So I've shown you three different steps, right? First step was just kind of going like this, then we had this parallelogram, then we go up with a cube, and now we just choose another direction, and we make a copy this way, and connect our corresponding points, and that's a shadow of a four-dimensional cube. And you can make these things yourself, and you can't basically go wrong, right? You just chase one direction, second direction, third direction, fourth direction. You just draw away, just autopilot, and automatically, whatever that might mean, I just take it from me, I'm going to produce a bona fide shadow of a four-dimensional cube. But we don't have to stop here. Huh? So we'll just go one step further, and we get a five-dimensional shadow. And we take it one step further, and we get a six-dimensional shadow. So that's a six-dimensional shadow. And that's actually pretty amazing when you look at it. It's actually a cube of a cube, right? So we've got like 1, 2, 3, like 8 little cubes, and they're connected up. And I've actually got a printout of this. So I printed this. See, these high-dimensional shadows, they actually also exist in 3 dimensions. So that's a 3-dimensional shadow of a 6-dimensional cube. So have a look at this one too. It's something pretty amazing. It might actually be that I've only shown this to 4 people so far, this particular one. Right? So other people have seen other shadows, but this is a very particular one. So you are very privileged in seeing the special Burkhardt shadow of a 6-dimensional thing. So, yeah. All right. Okay, so I think we'll probably start thinking about finishing up. So I just want to show you one really nice trick for you to spring on your friends. So you've got one party trick already that's asking them how many sides of the cube you can see. Here's another one. You can play this anytime you have a CD with you or a coin or anything. So what you want to do is you want to take a CD and draw a circle. Just draw one. And then you draw another circle that intersects this one here. So now these intersect in 2 points. There's one, the other one we don't care about at the moment. Now we take the CD again and make another circle that intersects the other 2 in exactly the same point as the one marked there. So now we've got three circles through that one point. And we've got 3 more points of intersection. Actually, Simon's a really, really nice guy. So he's been supporting this from the very beginning. Without Simon, there wouldn't be any lectures. There wouldn't be many of the things that we're doing. So every once in a while I have to take the opportunity to actually thank him for stuff. And today he even brought me a new lightsaber. It's just amazing, this lightsaber. I've been running around with these 2 for years. All right, this one is a really good one. And it even, it's got different patterns. This is fantastic, right? Yes. Okay, now, Simon's lightsaber. We've got another point of intersection here, another one there, another one there. So 3 points of intersection. And now, there's something really amazing, and this is that if you now take your CD, no matter how you start it, you can actually fit a circle the size of the CD through those 3 points always. There could be anything. I mean, 3 points in the plane, so 3 points in the plane, if you take any 3 points in the plane, there will always be a circle that kind of fits through them, unless they're in a line, which is a big humongous circle. Okay, 3 points in the plane, you can always fit a circle through them. But with those 3 points that are produced just like this, the circle is always going to be exactly the same size as the surface that you started with. So, pretty amazing. Okay, I want to show you why this is so. And it's actually mathematical proof. And it's going to have a cube in it. It doesn't look like a cube, but there's going to be a cube in there. So, let's have a look at this. So, there's the circle that goes through them. All the circles are the same size. All right, let's start. So, first thing I do is maybe this one. Second one. This is quite nice. Okay, so we put a radius in, right? We put a radius in for that red circle. We put another radius in for the green one. So this green one going into the middle, and here for the blue one going into the middle. If you just focus at those 2 guys, we can put 2 more radii in. And that gives you a rhombus automatically. It's kind of completely automatic. It's going to be a rhombus. Okay? So they've got a rhombus. And they have got another rhombus. And they've got another rhombus. And now let's just put all 3 in. And what starts appearing here? It starts appearing a cube. So what we started drawing here is basically a cube, and you can easily complete it now. So there, it's completed. So there's a cube. So that's the center of the circle that's going to go pass through all of those 3 points. And it's also easy to see why, because all these connections have the same length, right? They're all the length of the radius of a circle, so they're all going to go through the same point. Proved by Q. Very unusual. All right. So this one good or not so good? Interesting. You're not going to be able to remember all the stuff. Which one are you going to remember from today? Tell me. Which one are you going to remember? So we just to summarize again. So first we had. It's all gone already. This is the hovering cube with the height being equal to the area, kind of. Right? The second one was the hole in the cube. Hole in the cube. That was good. Then the third one was, which you can still remember. How many faces does a cube have? Yes. 6. All right. Anyway, I think we'll finish up now. I've got lots more stuff, but you're probably all at the stage where you kind of you've had your dose of cubes today, and maybe you want to ask some questions or maybe just play around with some of these things. Rob, is it okay if people touch your models, or you'd rather have them admire them from afar?
Yeah.
Admire them from afar.
Under supervision.
Under supervision. I mean, these are very fragile, right? So these are very fragile.
I mean, they're just made of paper.
Yeah, just made of paper. So basically, if you squish on it, it's going to be a flat model.
Quite as fragile as
Yeah.
anything made of paper. Once you put a few folds in it, it kind of makes it completely. But
Right.
that's good.
But anyway.
Actually, some piece went up as well.
Yeah. Anyway, let's finish up with this, and I hope you. Oh wait, let's just go back one step, and we've got a. Oh yeah, maybe just tell you what is all this is good for. Okay, so in the future, there's actually going to be an alien spaceship that visits the solar system, and at that point in time, it's going to be very, very important to know the weaknesses of the cube. Right? So I mean, I've kind of started now. But basically there's going to be a final battle, and if you follow Star Trek before you see the final battle, it basically looks like this. So there's going to be the cube. Right? And now, if nobody knows anything about the cube, I mean, we're lost, right? We're lost. But so luckily, in Starfleet Academy, they teach stuff about cubes, right? So here, Picard has somehow located a weak spot, so they're all targeting now the weak spot. And let's just see whether what happens. All right, victory. Well, there's something else going on here with the sphere escaping, but it's the next talk. Well, sphere, the dark side of the sphere, right? Anyway, with that, I'll finish this presentation. Hopefully, you've got something out of this. And if you're unsure, I mean, if you've half forgotten now what all the facts were, just send us an email. You find an email here at qed.com. And I'll probably make the video of this presentation available online, and also parts of the talk if you want it. It's not a big problem. So just let me know and I'll send it to you. So thanks a lot for coming today, and come again.